In the quiet suburbs of New Jersey, there stands a massive brick and glass structure that functioned as the nervous system for the 20th century. This is Bell Labs, the research arm of the American Telephone and Telegraph Company. For decades, it was the only place on Earth where a physicist might bump into a mathematician or a chemist while walking down a corridor nearly a quarter-mile long. It was designed specifically to foster these chance encounters, operating on the belief that fundamental science and practical engineering should never be separated. Before the late 1940s, the world of electronics was fragile and hot. If you wanted to amplify a signal or switch a circuit, you relied on vacuum tubes, glass bulbs that looked like light bulbs and acted like them, too. They were prone to burning out, consumed massive amounts of electricity, and generated immense heat. Bell Labs realized that if they were to build a nationwide telephone network, they needed something smaller and more reliable. They turned their attention to a group of materials known as semiconductors, which could conduct electricity under specific conditions. In December 1947, John Bardeen and Walter Brattain, under the direction of William Shockley, demonstrated the first point-contact transistor. It was a crude-looking device made of gold foil plastic and a small slab of germanium. Yet, it did exactly what a vacuum tube could do without the heat or the glass. This small component allowed for the miniaturization of electronics, eventually leading to the billions of transistors etched into the silicon chips inside our pocket devices today. It wasn't just a better switch, it was a fundamental shift in how we manipulate matter. While the physicists were tinkering with hardware, a mathematician named Claude Shannon was rethinking the nature of communication itself. In 1948, he published a mathematical theory of communication which introduced the concept of the bit. Shannon proved that all information, whether voice, text, or images, could be represented as a sequence of ones and zeros. He provided the mathematical framework for data compression and error correction, ensuring that messages could travel across noisy channels without losing their meaning. This theory remains the foundation for every digital transmission occurring in the world right now. Bell Labs also looked toward the stars to solve problems on Earth. In the 1960s, Arno Penzias and Robert Wilson were using a large horn-shaped antenna in Humble, New Jersey, to track radio waves from space. They kept picking up a persistent background hiss that they couldn't explain. After ruling out every possible source of interference, including local radio stations and even pigeon droppings inside the antenna, they realized they were hearing the faint afterglow of the Big Bang. This discovery of cosmic microwave background radiation transformed cosmology from speculative philosophy into a precise, measurable science. Long-distance communication faced a physical bottleneck. Copper wires could only carry so much data. Bell Labs researchers pushed the boundaries of material science to develop high-purity glass fibers that could transmit information as pulses of light. This led to the development of fiber optic cables, which now line the floors of our oceans. Unlike electrical signals in copper, these photons could travel vast distances with minimal loss. When combined with a laser and other technology significantly refined within these walls, the result was a global network capable of moving an almost infinite amount of data at the speed of light. In 1954, three researchers at Bell Labs, Darrell Chapin, Calvin Fuller, and Gerald Pearson, created the first practical silicon solar cell. Before this, converting sunlight into electricity was inefficient and largely a laboratory curiosity. By diffusing impurities into silicon wafers, they created a surface that could generate a significant current when exposed to light. While initially too expensive for home use, these cells found their first major application in powering satellites. This breakthrough laid the groundwork for the renewable energy industry, proving that the sun could be a direct source of power for human technology. The innovation wasn't limited to hardware. The labs also redefined how humans interact with machines. In the late 1960s and early 70s, Ken Thompson and Dennis Ritchie developed the Unix operating system and the C programming language. They wanted a system that was flexible and portable, rather than tied to one specific type of hardware. Today, the descendants of Unix power everything from the servers running the internet to the operating systems in our smartphones. By creating a standardized way to write software, they provided the tools that allowed the software industry to scale globally. What made Bell Labs unique wasn't just the funding, but the culture of open doors. The building was designed with incredibly long hallways so that researchers would be forced to interact with people outside their specific fields. A chemist might offer a solution to a problem a physicist was facing, or a linguist might help a computer scientist understand speech patterns. This cross-pollination of ideas was managed by leaders who prioritized long-term discovery over short-term profits. They understood that you cannot schedule a breakthrough. You can only create the environment where one is likely to occur. Today, the era of the giant industrial lab has largely faded, replaced by the fast-moving startups of Silicon Valley. However, the blueprint established at Bell Labs remains relevant. It showed us that the most significant leaps in technology happen when we invest in basic research, asking questions about how the universe works without knowing exactly how the answers will be used. As we face new challenges in quantum computing and artificial intelligence, we look back at this New Jersey building to remember that the future is built by giving brilliant people the space to be curious.
If you'd like more videos like this, you can subscribe and come back to Brief Stories anytime.